Hello, everyone, and welcome to the June 2026 LINCC Talk. My name is Olivia Lin, and our co-host is Colin O'Ryan Chandler. We're both members of the LINCC Frameworks, I as a software developer, and Colin as a project scientist. I'm at Carnegie Mellon University, and Colin is at the Dirac Institute and the University of Washington. LINCC Talks include presentations and demonstrations that showcase work done by the broader Rubin software and archives community with the goal of further enabling LSST science. Unlike traditional talks you might hear at a conference, here we highlight the technical aspects of the work being done. We hope these talks provide a useful forum for a range of groups and authors to present, learn about, and discuss efforts of interest in the analyses of LSST data. LINCC Talks are delivered virtually every second Thursday of the month at 10 a.m. Pacific, 1 p.m. Eastern. Our speaker today is Weixiang Yu, who is a postdoctoral fellow at Bishop's University. His research focuses on AGN variability and its use as a probe of accretion flows around supermassive black holes. For the talk, please ask questions in Zoom or in the LINCC Talks channel of the Discovery Alliance Slack. On Zoom, you can type questions into chat or raise your hand. As a friendly reminder, these talks are being recorded and they will be posted on our YouTube channel. With that, Weixiang, please take it away.
Is my screen okay?
Yes, yes.
Okay, thanks. Hi, I'm Weixiang. It's a really great honor to give a talk on our recent work, EzTaoX, here for scalable and flexible multiband modeling of agent light curves in the Rubin era. This work is done as part of a Canadian contribution and supported by the Dunlop Institute for Astronomy and Astrophysics at the University of Toronto. So also in collaboration with multiple people, including John Run, Colin Burke, Jennifer Lee, and others involved in the LSST AGN science collaboration. Okay, so what does the AGN, the name refers to as is active galactic nucleus. Typically, we use that to call a bright nucleus at the center of massive galaxies, which we believe is powered by massive black holes accreting matter onto themselves. And black holes typically weigh above 10 to the 6 solar masses, even up to 10 to the 10. By doing so, the accretion process emit a lot of energies across a wide range in wavelengths. So if here on the bottom shows a multi-wavelength spectrum of an AGN. So basically, it just plots the distribution of energies emitted by AGN as function of here is frequency, but also relevant is wavelengths. So over years of intensive multi-wavelength study of AGN, I think we have built a pretty solid static picture of AGN, for example, its structure and where does the lights coming from in the accretion flow. On the top, I'm showing a schematic plot for AGN, what we think it looks like. Right, so here, for example, is the black hole, and near is actually corona, which is powered by hollow plasmas, and that corona emits mostly in the X-ray, as you see down here, and it going further, there's a disk which pulls matter in, and when it falls in, it spirals onto the black hole and form a disk. And the disk primarily emits in UV and optical, which give you this blue bump here. And on above and below the disk, in the outer edge of the disk, there is called broadline region, which is, gas and a cloud of gas, and that are responsible for giving rise to the emission lines you see here. And then the furthest is like dusty torus, which emits mostly in the mid-infrared regime. So what we have learned not only is which part of the accretion flow emits in what part of the spectrum. We also know a lot of physics that are involved For example, the physics needed to give the specific shape of the X-ray spectrum, the physics needed to give rise to the emission lines, and the physics needed to give the mid-infrared emission. However, we know a lot less about the physics needed to drive how AGN behaves in the time domain, for example, as function of time. But we do have is some good data for a few very close by AGNs that has been intensely monitored. What I mean by that is you measure the brightness of AGN over a very long time, for example, every single day for a year, and then you can get a light curve for AGN. That is what's shown on the left. The x-axis give you the time, the y-axis in each panel give you the flux of the AGN. And from top to bottom, the energy of the photons we collected decreases. So from the light curves, you might notice a few features from it. One is the flux of the AGN varies, and in a more stochastic, we call stochastic, but like a random manner. There's not like a sine wave or like a supernova. It goes to explosion and fall off, right? It's very random. And then they're correlated across wavelengths. So if you look at the shapes, there are more or less matches. And there are interband legs, which we call each panel a band. It refers to a specific wavelength. So it's hard to see by eye, but I draw a vertical line here just to guide your vision. Here you might see this dip here, and then if you move down to longer wavelengths, which with lower energy, you see the dip actually shifted to right, which we call this interband time lags. And that's basically that's the best picture we can build for the temporal behavior of AGN. Just to be clear here, no physics involved yet. So when you take a Fourier transform of one of the light curves, you also see some additional features, which we call this, once you take a Fourier transform, we call this as power spectrum, which describes how does the variability power energy distribute across frequency. We should see this characteristic shape, which give the power decreases as you go into higher frequency and smaller time scale, and also has this kind of a characteristic shape where it is a break, which we call this time scale like damping time scale, and if you go the longer time scale, we go and a smaller frequency, the power stables, which basically translate into the variability amplitude of the light curve stop increasing, right? Models, there's a specific model that describes this shape of PIC. It's called dampened random walk. I'll come back to this name more frequently in following slides. Again, for the temporal behavior of AGN, we have some very good characterization, but we do lack a lot of data to understand the physics that's underlying physics that are driving this behavior. And also, there's a lot of work on the theoretical front to help us understand why it varies like this. Nonetheless, many works have shown that by modeling AGN light curves as a damped random walk process, we can, use it for a lot of sciences. Specifically, here shows the power spectral density you're showing in the earlier slide of DRW as parameterized in this insulated function, which by two parameters. One is like short-term variability amplitude, and another is the damping time scale, which is the break you see in the earlier power spectral density. One you can do is by fitting light curves as DRW, you can select AGNs out of astronomical sources observed. When you first take an image of a source, you have no idea what it is. But if you can fit its light curve using DRW. You can clearly select AGNs from all sources. Here it shows the distribution of AGNs and stars in the DRW parameter space. Y-axis is the time scale. On top is the distribution of AGNs, and the bottom is distribution of stars. In addition, you can perhaps use the time scale as a um, rough or crude estimate of black hole mass. More recent work from Colin Burke 2021 showed that the damping timescales correlates with a black hole mass, right? Which can be super useful for future like upcoming surveys like Rubin LSST, where you don't have the spectrum necessary to give you the black hole estimate, but we do have light curves, right? Um, so hopefully that's give you a rough idea of what we know about AGN variability. Now let's move on to Rubin, because this is a Rubin talk. So Rubin is great. What Rubin is, just briefly, is basically you holding a big camera and scanning the sky and making pictures and then turning them into movies. Rubin will scan the whole southern sky like 800 times, and for a few really we call deep drilling fields, like small fields, you even observe it for 1,000 times. No, 10,000 times, sorry, for 10 years. It also has a wide wavelength coverage, cover almost the whole, like near UV to near infrared. So that give you like 6 band passes, which is ideal for study AGN multiband AGN variability. We can use that to understand how does the variability changes as function of AGN physical properties. Again, because Rubin goes so deep, we can see detect somewhere around like 100 million AGNs, hopefully. If we can derive a good correlation between variability and AGN physical properties, we can use like black hole mass and anti-ring ratio derived from variability to study AGN evolution. Okay, hopefully you're all convinced that we should do this using Rubin data. However, there are some challenges. One, it's good we can see 100 million AGNs with Rubin, but we don't have the tools that's necessary to fit those light curves. We need faster tools. Second, the cadence is suboptimal. I said it's 800 visits, but it's split into 6 bands. When you're looking at only one band, the cadence is not that great. It has like a 20-day internet gap. This is for G band. This derived from the baseline 3.4 simulation cadence. However, if any algorithm that are able to combine it from all 6 bands, you eventually will get this 3-day cadence, which is perfect for most of the AGN variability signs. So what we need from here, or for Rubin, is we need something that is a tool that's scalable and at the same time doing multi-band fitting on AGN light curves. And there's no such tool exist. That's where EzTaoX come in. The goal is to scalable multi-band modeling of AGN light curves. You can scale using Gaussian process. Okay, so first, what is a Gaussian process? I will use one sentence to summarize this. I think Gaussian process is a collection of Gaussian random variables, and for each Gaussian random variable, you assign a timestamp to it. Also, you use some kind of covariance. The covariance between any 2 Gaussian random variables is described by a kernel function. Here on the left, show example of a fit Gaussian process fit to a time series. Here, like a few data points. We mentioned this observation is a random Gaussian variable vertically, and then any other of the 2, if you plot their covariance, here is shown as this. Like you might have recall, you have 2 2D Gaussian random variable. Their distribution will look like this. Since it's all probabilistic, it is also describes as a distribution over functions, because you can always draw random samples from joined multivariate Gaussian distribution. And then that will form like a distribution over functions, as you see as this arrow snakes. Okay, once we can put this in this Gaussian process framework, you can easily evaluate the likelihood of you know any Gaussian process model given the data, and all you do is to optimize the likelihood, give you the parameters which encoded in here is the kernel which describes the covariance between any two data points, as I referred earlier. So to find the best fit parameters, and that will give us meaningful information about AGN variability. Again, why we want to use Gaussian process, because the statistical models we use in previous studies to analyze AGN light curves can be expressed as Gaussian process, for example, DRW. Okay, how do we do multiband? The way we do it is we assume the AGN light curve in each band is a scaled and shifted version of some latent Gaussian process. Here, the covariance structure of the latent Gaussian process is described by this kernel function. And here, if you pick any two bands, there's always a time lag between them. This is used to model the time lag we see from real AGN light curves. Here you see this. You can visually see that the first band is in blue, second band is simulated data, second band in orange, and there's a shift between those two. We see the peaks. I have marked them with these arrows. And the S1, S2 describes the scale of the variability. S1 for the second band, you see this like smaller variability, and the blue for the blue described S2. Oh, sorry, this is reverse. But anyways, the orange ones correspond to the orange light curve, has a smaller variability amplitude, and the blue one, the blue arrow, describes the blue light curve, which has larger variability amplitude. If we put using this framework, we can connect light curves in different bands and model them simultaneously to both infer parameters of the latent Gaussian process, for example, DRW, and its relative scaling factor, and also the lag between different bands. And for implementation, we have taken advantage of the celebrity model from Denver Mackey and implemented in JAX. The specific package we use is called TinyGP. What it does is give you the the O to the n scaling for likelihood evaluation. For typical Gaussian process, it follows O to the n to the power of 3, where n is the number of data points in your time series. In addition, since it's done in JAX native support just-in-time compilation, automatic differentiation. What just-in-time compilation does is it will, when you first time run the code, it compile it into machine code, and then for future evaluations of the likelihood, you basically run this on compiled code. This is particularly useful or ideal for the work we do, like doing model fitting, because you might evaluate the likelihood function 10,000 times, or like sampling Monte Carlo, Markov chain Monte Carlo, right? And automatic differentiation is you basically write your likelihood in a differentiable manner, and it will some sampling algorithms or perhaps optimization algorithms and take advantage of that the derivative information to speed up the inference process. Both of them going to give additional speed up to the O to the n scaling. Lastly, JAX has a very good ecosystem that has already implemented a lot of the optimization algorithms for maximum likelihood fitting, or sampling algorithms for doing sampling like Monte Carlo, Markov chain Monte Carlo MNC, or nested sampling, for example, using Jackson X. Next, I want to show a few science cases we can do with EzTaoX. You may recall from earlier, people have shown that the damping timescale of the DRW model correlates with black hole mass. And we found that multiband fitting greatly improves the inference of the damping timescale when the intrinsic timescale is very small. Here I'm using simulated LSST DRW light curves to demonstrate this. The x-axis give you the true DRW timescale, and the y-axis give you the recovered DRW timescale. And if you look at this blue shaded region, give you the distribution of the recovered ones for if you only use U-band data, and the green one shows the distribution if you only use G-band data. And this yellow hatched region shows the distribution if you use U plus G light curves. You can see that you cannot recover intrinsic DRW timescales, perhaps somewhere down to like 10 days, and with single band data, with single band light curve, but you can with multi-band approach, right? Why it matters? Because this correspond to a black hole mass range from like 10 to the 4 to 10 to the 6.5, where this is a huge and explorative gem in terms of both the study of AGN and also its variability properties. So by using our multiband approach, we can enable characterization of UV optical variability of like low mass AGNs. Also use it as a way to select AGNs, so we can probe the demographics of those AGNs. And secondly, we test how well it can recover the interband lags, as we have seen from first slide, is a defining feature of AGN multiband variability. Again, we use the simulated data. This like the sigma DRW tells you how variable the AGN is, and this give you the damping timescale I have talked about earlier. And here GNR give you the depth, the simulant magnitude, like how faint the source is. So before EzTaoX, everybody uses it called Javelin. So we first see how Javelin does. Here shows x-axis give you the input lag between only two bands, like GNR. Y gives you the difference between them. So if it's 0, that's the best recovered, right? So and the top panel shows the distribution of the delta lag. If you only use 3-year LSC light curves, that's all. Know that it's all Y-fast steep, no DDF, and this is used 10 years light curve. And here is our results from EzTaoX. You can see that they're mostly comparable. In some cases, it might do slightly better. Okay, why do we care about precise recovery of the lag? One reason is the current mainstream model explaining AGN UV optical variability is that the AGN disk, which here shows here, the disk doesn't vary much, and it's the accurate corona which is the closest to the black hole varies a lot, and the high energy photons coming from the corona will shine the disk, and the disk reprocess that high energy accurate photon and re-emit in UV optical. If that's the case, the lag basically translates into the time traveling distance between the corona and the disk. We can use that time lag between bands to measure accretion disk sizes. However, there's a lot of debate about that, and some more recent monitoring of close by AGNs shows that the lags are longer than what's predicted by the current understanding of accretion disk. So by measuring this lag, we can further test accretion disk models, as well as uncover what is actually driving the variability we see in the UV optical wavelengths. The last science case I want to demonstrate is EzTaoX. There's something is still preliminary or testing using the multiband the capability to do to search for quasars exhibiting periodic variability. Why look for those? Because by the current nominal hierarchical formation his theory of galaxy, we know that if two galaxies have their black hole in the center, when they merge, their black hole should also merge. That's going to form a supermassive black hole binary. And if the binary is also actually creating, which emit a lot of electromagnetic radiation, we should expect them to exhibit quasi-periodic or periodic variability due to different physical mechanisms, such as accretion modulation or some geometrical effects. And so we have done simulations to understand if we can actually do that. The way we simulate is we simulate sinusoid light curves, and on top of that, we add DRW, which describes the variability due to the intrinsic black hole accretion. So here it shows the input sinusoid variability, and this is the downsampled light curves like at LSST wide fast steep cadence and GNR I band. Note that they don't completely match because we've also added DRW variability. In the past, people always use this LINCC to search for periodicity from AGNs. However, the LINCC paradigm assumes a white noise at the null hypothesis. So any peak you detect is on top of like white noise, but most AGNs exhibit stochastic noise, something like a DRW, right? And that when you use LINCC, that gives you a really high false positive rate, right? You cannot distinguish between if the peak is due to DRW, which is the stochastic, was intrinsic to AGN accretion, or it is due to the binary accretion, the binary dynamics associated with a supermassive black hole binary. So in this way, what we do is we use two kernels to fit the simulated light curves. One is a DRW, another is a Lorentzian. I won't go too deep into that, but the Lorentzian is can use to model both periodic and quasi-periodic variability by enlarging or shrinking this width of the Lorentzian peak. So here in blue, it shows the recovered power spectrum density for the DRW part, and the orange shows the recovered Lorentzian power spectrum density. And you can clearly see that here the Lorentzian peak well matched with input true period, which is shown as the vertical dashed line. We're still in the early stage of testing this. Hopefully this will give us promising results. And I haven't shown a lot of science cases. Honestly, most of them can be done without EzTaoX. There's tools out there that can do those stuff. But what others cannot do is doing that in a scalable way, which is critical for Rubin, because we're gonna work with tens of millions of AGNs, right? Even hundreds. So here I'm just demonstrating how fast EzTaoX is, and the X on the left shows the benchmark result for each likely evaluation as function of number of data points in your light curve. We are again comparing against Javelin, which another tool also does DRW, simultaneous DRW and lag measurement. This purple curve shows the performance for Javelin, and the orange or brownish curve shows the performance for EzTaoX. And you can see that's a 30 times to 2,000 times faster. And if you look at the for wide fast steep, which is shown as the blue box, it goes like 300 to 100 times faster. And for deep drilling field, it's yellow, it's like 2,000 times faster. But I want to remind you that this only per likelihood evaluation speed up. There is more speed up you can gain by taking advantage of the differentiability of the likelihood, right? Some sampling methods uh, um, will has provide even further speed up by using the derivatives. So in the end, you're looking at a 100,000 times speed up for WFSD light curves, 10,000 speed up for DDF light curves. And if I do the math, like about like 20 seconds per light curve, and for 6 bands, you're looking at like 60K CPU hours for 10 million AGNs, which is completely doable. Now I want to talk to you about the LINCC Incubator Program, which really, I would say, helped us to bring this tool to the next level. For the LINCC Incubator Program, Jennifer Lee is the PI, and Colin Berg and I was like joined all together to work on the code. I think the first thing they've done significantly is really adopting a lot of the best software engineering standards and practices. For example, testing, linting, automatic documentation, benchmarking, and automatic pipe release, as well as a lot of profiling of the code. I think those really makes EzTaoX a community software, which ease the way for future contributors to join this project. Others have done is integration with some link infrastructure, for example, LSDB and Liker links. By integrating with LSSDB, we can easily parallel EzTaoX fitting over many Rubin light curves. And the integration of light curve links allow us to do a realistic LLC simulations of AGN light curves, and which in the past I have done it. Gonna takes a ton of time. Lastly, we have through this program we have developed new kernels, which I will talk about. Is more physically motivated kernels for AGN light curve modeling. Okay, first the incubator. The first I will show highlight is integration with LSDB. The incubator team has helped us, put as either a notebook, also like our PI Jennifer Lee was involved in this, basically demonstrating that you can use EzTaoX with LSDB on DP1 light curves, right? So here is a short video recording the notebook. So this is all run within the RSP, right? So now you load the light curves because the light curves are already pre-processed. It's very there is like 1 million light curves is loaded, and here shows some cleaning. We often do remove some nuns on like bands and do a signal clipping. And then all the functions, there's all to do that. And this part defines the EzTaoX fitting. And next, you just wrap everything together into this run EzTaoX function. And this you call map rows. It do lazily. It doesn't do anything yet. Remember all the function before. Now it's wrap around into this function. And then you hit run, and it will take care of everything and do all the cleaning and fitting for you. And then it stores the data into this pandas data frame. You can also reload from saved MCMC chains. This is a quick function, helper function to visualize the results. Here, the light curve, the fits, and distribution of the parameters. I think this is a trace and posterior. I would like to note that this is a DP1 light curves. It's, I don't know, a few weeks on, so it's hard to get something physically interesting. But the framework is set up through this incubator. Another one I want to highlight is the integration with electro links. So people might be aware there's new Rubin simulation 5.3 with the integration of the electro links. A lot of the evaluation of the cadence, if we require starting from simulating light curves, it will be done a lot more easier. Here's again, they kindly put together a notebook and demonstrating how to do this. The first now is creating some fake survey data like 3-day cadence, but eventually we will load it from the pre-produced Rubin cadence and create a what kernel. This is the DRW kernel you want to use to simulate the light curve. And here's some parameters. Here is using this function is actually sampling from a random distribution, but I think you can also put in fixed numbers. And here it defines how bright the source is. Either you can do a fixed number or you can do a distribution, and where you should sample the source at, right? RN deck. And then you put all of them into one function and specifies those parameters. And then you can just this is showing that if you hit every the time, it will give you a different parameter because it's a random distribution. And then you just simulate. And then simulated 5 light curves at 5 different area deck, I believe. Here shows the light curves is returned into a pandas data frame. They're showing like 5 different locations associated with each simulated light curve. And here's some example of the simulated light curves. Okay. Lastly, I want to mention is through the incubator program, we have developed physically motivated GB kernels for reverberation mapping. It's just another name for measuring the lags between different bands. Recall the earlier picture of this lamppost model where the AGN variability in UV optical is driven by the X-ray corona. If that's the case, the lag, the time delay between between the X-ray flux variability and the UV optical flux variability is no longer a constant shift, right? It's actually a convolution of the X-ray time series and some transfer function, which is shown on the left, right? Which describes a distribution over lags rather than a fixed lag. And mathematically, this can be formulated into this function where this y drive gives you the time series of the X-ray light curve, and here is the transfer function. And then when you do the convolution, you get the light curves you observed in UV optical wavelengths. Why this is critical? Because based on this model, the transfer function changes as with the physical parameters of the AGN, like the black hole mass, the AGN ratio, the wavelengths you're looking at. In this particular case, I'm showing actually the shape, which has the most, in my opinion, dramatic changes. The shape depends on the viewing angle of the AGN, right? So along the angle between the spanning axis of the AGN here and your line of sight, right? So by folding those into our modeling approach, we can simultaneously infer the actual shape of the transfer function, and allowing to perhaps infer the physical parameters of the AGN. Okay, and then while at this incubator, we realized this. Although this is a convolution in a time domain, you can fold that into the kernel space, right? You can write out a kernel that actually describes a convolution between this driving signal and this transfer function. So basically, we tested this using a DRW and a Gaussian transfer function. This is mostly done by Costa and Collenberg. So the way we validate this is using something called a structure function. It's just another way that you can easily compute those from simulated light curves, and which also describes how does the variability distribute over time. If you remember, PSD describes how the variability distributes over frequency, but structure functions over time. Okay. So this is just this shows how you would compute numerically the structure function using similar light curves. Shows how you would compute the structure function based on the kernel. What I'm trying to show here is this curve down here. Black shows the choose one from the kernel, and the red and then the green one shows the structure function that we computed numerically from simulated light curves. We've also done two kind of simulations. One we simulated directly from the kernel using GP. Another one is simulating some driving signal and numerically convolve that with a transfer function and get observed light curve, and then you compute the structure function from it. You can see both agrees well with our theoretical structure function. And here it shows the input DRW structure function. Okay, so quick takeaways. I think EzTaoX enables scalable, flexible multiband modeling of AGN variability in the Rubin era. Application of EzTaoX to Rubin light curves will allow many interesting AGN sciences, ranging from classification to testing of accretion models, inference of fundamental AGN properties using photometric data. And EzTaoX is still under very active development. We welcome community feedback, testing, and contributions. You can find EzTaoX at this GitHub link. Lastly, massive thanks to the LINCC Frameworks team for their extensive support, which has really bring this software to a new level. Thank you, everybody, for listening, and happy to take any questions.
Thank you, Weixiang. And we do have time for some questions. Feel free to ask by raising your hand here on Zoom, asking in the chat on Zoom, or in the chat on the LINCC Talks channel. Let's start with Colin.
Hey, thanks. That was a really fun talk. Appreciate that. I have a couple questions, but I think the main one I'm curious about is sort of the rollout timeline and how you plan on doing that in terms of LSST when their data comes. So you mentioned DP1 is sort of like a test bed. What is the strategy for sort of running the code? Do you imagine that you'll run it like a daily, weekly, monthly, or just for DRs? And if you can run it with earlier products, like looks like you got somewhere with DP1. How soon do you think you can start producing results? I know, sorry, it's a long question.
Yeah, I appreciate that question. It's more of I see more of a compute resource problem than a plan problem, right? Like the plan, we want to do it probably not daily. It might be useful for a selection of objects if you want to look for like transients or like chain log agents, stuff like that, which produce fast variability. But I think we're more looking at doing this on DR light curves, where for both classification purposes and for doing like inference of fundamental properties, just characterization of those. Yes. And this, based on the current allocation of computer resources to individual users, this is going to be a limitation. But we do have plans to put in like joint proposals for computer resources as part of the AGN collaborating as a group to hopefully make that happen.
Okay, you opened the door a little bit, so I just have to follow up and ask what kind of resources are you wanting or needing, and what's it taking right now?
Yeah, so all the speed I was showing is on CPU, so we only need CPU. And basically, I mean, for each DR, depends on okay, I don't have a rough number on how to say that. For classification, depends on how well we can make preliminary cuts based on color. And then you can proceed into variability modeling to do better selection. I don't have a good number on top of my head there, but I will say if we want to do that, we're looking at a few million CPU hours for the 10-year light curves. But if you have like 1 year and 2 years, that's a lot smaller. I'm only speaking about a 10-year light curve. And for purely variability study, once you select those AGNs, photometrically select them, you can cut them down to like maybe 1 million CPU hours. That would be good enough for 10-year, right? And you can shrink that down accordingly based on the data sets. And perhaps for some really good data, like in DDF, you want to do more sophisticated modeling, but the size is a lot smaller. We're not expecting to get a lot of AGN. It is a lot, but not comparable to WebFast right? Maybe, don't call me on the number. I mean, 500,000 AGN, 500,000 speed hours would be good enough, right? Right. Yeah.
And you mentioned with LSST, there will be too many light curves. We'll need faster tools and algorithms. What would you say are some of the changes made that you think were the most impactful towards achieving these higher speeds?
Yeah. So I would say two things. One is adopting this celerity model, which has the n to the O to the n scaling. But at the same time, you see that for WebFast, the 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 speed up is like 30. It's a lot, but not that, maybe not that a lot. What's in addition on top of that is the adopting of the JAX framework, which allow you to do faster sampling, which we do want to do faster sampling, because our analysis procedure always you do perhaps a maximum likelihood fit to see if the numbers is reasonable, and you do want to do a second step is doing sampling and to get to infer the uncertainties of those parameters. And to make meaningful scientific uses. So both of them added together to make this physical, make this plausible.
Yeah. All right. Thanks again for the fantastic talk, and thank you to everyone for attending the Link Tech Talk series today. Our next Tech Talk will be scheduled for July 9th. Stay tuned for an announcement. We'll be hearing about GoPro from Craig Pellegrino. In the interim, please join the LSST DA Link Tech Talk Slack channel and the link at list.lsst.org mailing list for more information and future announcements. There's more information, including links to the Rubin Community Forum and a calendar at our LSST Discovery Alliance website. LINCC Frameworks is also holding office hours every Thursday at this same time slot, except when it conflicts with this Tech Talk series. If you have an idea for a talk, we'd love to hear from you. Feel free to reach out on the Slack or by email listed on the Tech Talk webpage. And with the speaker's permission, today's Tech Talk will be available on our YouTube channel within the next few days. Thanks again, and have a great rest of your day or night.
Awesome. Thank you.
Thank you.